Hello, presentation. This is day 9, and I have changed to do what you asked me to do, students. I have changed the format of what I'm doing with these videos. We were just going to do like 90% examples in these videos. So let's get with it and look at a bunch of examples on exponent simplification, scientific notation, and radicals and radical simplification. So let's get on with it. Here we go to our sketch pad, and let's just see what we're talking about, right? We're going to talk about exponents. We're going to talk about, like, those will be problems like, x squared times x to the 6th, or some of the easier versions. And then some of the harder versions will be stuff like x to the -1, y squared over z to the -2 to the 4th times xy to the 2nd z cubed, something like that. This is the easier version towards the more difficult. Scientific notation is, we heavily use this notation in science to represent numbers, and we also do things like we can multiply those numbers together, as well as, so we can multiply numbers in scientific notation, and then we can divide numbers in scientific notation. And then finally, radicals and radical simplification is examples like, square root of 20 equals what? You got to simplify this. It gets more complicated, 1 over the square root of 16. More complicated is the square root of 2 over 3. And then more complicated is, 4 times the square root of 2 times 6 times the square root of 6. So this is what we're going to work on. We have lots of examples. What I want you to do on each one of these pages is I want you on each page to start by pausing and trying all of the examples on the page. With every new page, pause and try. And then I'm simply just going to work the problems, and we'll work them in green. Okay, so I assume you've paused and tried this. This is simply x, and this is the product of powers rule, is 2 plus 5. So that's just x to the 7th. This one here, we can rewrite it. We can rewrite it using commutative property. Right? We have 3 times x times 4 times x to the 4th. We can rewrite it, and we can get 12x to the 5th. This one we can do is, it gets a little more complicated, but it's pretty much the same thing as the top one. We multiply our coefficients, and then we multiply our variables. And you can group the variables like this, and you can end up with 52 a to the 4th b cubed. Here it gets a little bit, we're looking at the quotient rule, but you can look, in the quotient rule is pretty much, you can just take each number that's the same, each base that's the same, and apply the quotient rule. So these are all listed in order. So this is kind of cool. The answer is simply, and we want all exponents to be positive. So let's see what happens when we apply our quotient rule. When we apply our quotient rule, we get 2 cubed x y to the -1. Well, we know that a variable to the negative power, y to the -1 is the same thing as 1 over y to a positive 1, which is the same thing as 1 over y. So we can write this guy as 2 cubed x over y, because we have to move that y. This has to move to the bottom, as it were. And then you can change the exponent from negative to positive. Here's an interesting one. We're going to use our rule again. And we're going to separate this out so that we have our x's by itself and our y by itself. now we can easily see our exponent rule here. And we can say that, well, this stays the same. We get x to the minus 2, and here we get y to the 4 minus negative 2. So we get x to the negative 2, y to the 6. Well, here our problem is we have a negative, so we have to take this guy and move it to the bottom to flip the sign. So x to the negative 2, y to the 6 is y to the 6 over x squared. Okay, good. So again, we're just doing samples. I'm not explaining the theory of math to you because that's not what you wanted. You got enough of that in class. You just wanted lots of samples. So if you need me to do more explanation in these videos, let me know in class. All right, here we go. These are more complicated. So this is the power of power rules along with the product of the power of products rule. So remember how that works. We take this exponent here and we multiply it by each exponent on the inside. And this has a hidden exponent of 1. So we get x cubed y to the 6th. If you want to do that longhand, you could have said, well, that's xy squared 3 times. You could have said, if you got kind of confused, you could have said, well, here's the definition of power. And so now we have x, x times x times x. We can rewrite all these multiplications times y squared times y squared times y squared, and then that equals our x cubed y to the 6th. Okay, let's move on to B. Well, we have a negative, negative exponents, getting a little messy here. But we can do the same multiplication. Don't worry about the fact that it's negative. And we're going to multiply down to get rid of the parentheses. And we get 2 to the negative 4, b to the negative 8, b to the 5th. Well, b to the negative 8, b to the 5th, we add our exponents. So that's 2 to the negative 4, b to the negative 3. Now, we can't stick here with these negatives, so we have to move these guys to the other side of the fraction. So let's put that over 1, and now we can move this guy to the bottom and this guy to the bottom at the same time as flipping signs. So we'll leave our 1 on top, 2 to the 4th, b cubed, and now we have positive exponents. Okay, this is a little bit of a mess as well, but we can do it just by applying our. Here we have another power of quotient, but a power of quotients rule going on here. So we can expand this guy, and we get x to the 4th over y to the 10th, and this comes down as just y to the 4th over x to the 4th. That's y to the 10th. Okay, so now let's put that together, and we'll say, well, that's x to the 4th y to the 4th over x to the 4th y to the 10th. Well, these guys cancel, and so now we get x to the 4th, y to the 4th over x to the 10th. Now look, there's 2 ways we can look at this. One, we can just say, well, that's y to the negative 6th, because that's 4, or that's y to the 4 minus 10. That's y to the negative 6, and then that becomes 1 over y to the 6th. That's one way you can do it. The other way you can do this one is you can say, well, there's 10 y's on the bottom and 4 y's on the top, so I just know that if I cancel, I could say that's 1 over y to the 6th. I could go straight there if I wanted to. If I didn't want to apply my quotient rule, I could just see that there's more y's on the bottom than on the top, and so there's 6 y's multiplied together on the bottom. Either way, up to you. All right, this is kind of a mess. There's a lot of ways we can go with this one. We can multiply across the top and bottom, or we can simplify within each fraction. Let's do the multiplication across top and bottom. Well, a to the negative 1 times a squared is a to the 1st. And then we have b to the 5th. If we multiply across the bottom, we get a, and we get b to the first times b to the negative 2. We add our exponents. 1 plus negative 2 is b to the negative 1. All right, now don't cancel these out and think it's a 4. We need to apply our rule. And we could just cancel our a's, but watch what happens. Let's do something different, and let's just use our quotient, or our quotient rule. A to the 1 minus 1, because right, this is like an a to the first over a to the first times b to the 5 minus negative 1, right? 5 minus negative 1. And so here we get a to the 0, b to the 6th, because that 5 plus 1. Well, anything to the 0 power is what? It's 1, b to the 6th. So our answer is b to the 6th. Keep going. Here we go. Exponents, a to the negative 2. Now we got the power thing going on. We're going to multiply down. Pause and try. All right, assume you've done that. So that's a to the negative 6, and that's equal to 1 over a to the 6th. If anyone wants to see some good videos on all of this exponent stuff, I have some other exponents from another class I did, and I can point that out to you. Hey, look, and I'm going to have a call out right now to Joseph. Hey, man, I'm going to put that link on this website by the end of today. The link to my webpage for Prez. All right. Now this guy is similar to other problems here. We just take our exponent on the outside and we multiply the exponent down. And what's the exponent of my 5? It's a 1, and the exponent of my 2 is a 1. So we have 5 to the negative 2 over 2 to the negative 2. Well, what do we do with these negative exponents? We don't like them. So we take the thing that's negative and we move it to the other side of the fraction. We take our 5 to the negative 2 and we put it on the bottom, and then we take the sign and change it to a positive. 5 to the negative 2 is same thing as 5 squared on the bottom. Same thing, if we have a negative on the bottom, negative exponent on the bottom, we can move that power to the top, and we can make it positive. Now, if you want to multiply that out, you can say, well, that's 4 over 25. Either one of these answers is fine with me. When numbers are small, multiplying it out is okay. But if these exponents are big, like 2 to the 10th, don't go making that 1024. I don't need you to do that. Just leave it as 2 to the 10th. All right, let's use our, all right, wow, all these negative exponents. But watch what happens if we take our exponent and then we just multiply down. Watch what happens here. This is really cool. Well, negative 1 times negative 2 is just 2. So we have x to the 2 on the top. Negative 2 times negative 4 is z to the 8th on top. And on the bottom, we get y, and the negative 2 times negative 2 is 4. And we have all positive exponents, and we're done. We didn't have to do much more than that. Pretty cool. All right, let's do the same thing here. Last problem with exponents. Boom, 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 boom. All right, we get a to the negative 2. We're going to have to do a little work now because we have some negative exponents coming out here. But we have c to the negative 6. And on the bottom, we have b to the 6th. All right. Well, we want to take this a and move it to the bottom, and this c to the negative 6 and move it to the bottom. So let's do that. We have b to the negative 4 over a squared b to the 6th c to the 6th. Well, now we can do two things here. Watch, we could use our power rule if we wanted to, or we could just move our b to the bottom. Let's try that. Let's just try moving our b to the negative 4 to the bottom without using our quotient rule. Let's not use our quotient rule. So watch this. So we'll leave our 1 on top, and then we'll get a squared, and our b to the 4th that we moved down, our b to the negative 4, when we move it down, becomes a positive. B to the 6th, c to the 6th. Now, we can't end here because we have two b's on the bottom, but we can combine them. by just what? Adding our exponents. So we end up with 1 over a squared b to the 10th c to the 6th. All right, so that's it for exponents, I think, yeah. Now we're moving on to scientific notation. Now scientific notation, I'm going to take a little time to explain scientific notation. I want you to tell me which numbers are in scientific notation. Again, we're not fully defining everything about scientific notation and deriving how we multiply and divide numbers in scientific notation in this video, because you guys didn't want that. You guys wanted lots of examples. So let's get those examples. Now when you look at a number in scientific notation, we can have an optional, A has to be, the other rule, by the way, is that you can have a negative number. Negative in front. You can have a negative sign in front. All right. So my A has to be, so it can be an A or a negative A. Can have a negative sign out front. All right, so A has to be between 1 and 10 after you take the negative away. You just look at the negative, decide if it's there, then you look at the A. And that has to be between 1 and 10. Now it can be 1, but it cannot be 10. Can't be 10, it's gotta be less than 10, but it can be 1. And then our exponent, 10, the exponent of our 10 has to be an integer. Now an integer can be negative, right? It can be like -2, -1, -10. Those are all integers. 0 is an integer, and it can be positive, 1, 2, 10, etc. So which one of these is in scientific notation? Well, this one is. This one's yes, because this is between 0 and 10, and it has a positive integer for an exponent. This number is not, because this number is too small. 0.4 is too small. This number here, yeah, that one is. It's got its negative in front. Its A is between 0 and 10, and it's got an integer for an exponent. So this one, yes. 10 times 10 to the 4th is no, not a scientific notation, because 10 is too big. It has to be less than 10. How about 6 times 10 to the 0? Is that okay? The answer is yes. 6 is between 0 and 10, and 0 is indeed an integer. How about this super long number times 10 to the 4th? Is that okay? And the answer is yes. It is okay, because it is between 1 and 10. This number is between 1 and 10, and our exponent is positive. Okay, so that's some examples of scientific notation numbers. All right, now we're going to do some examples of multiplying and dividing some numbers in scientific notation. Now, if you remember from class, the way that you do it is you multiply the first part, and then you add your exponents. And we showed you why that's true in class. So if you do that, because what's the idea? The idea is this 2.0 times 3.0 times 10 squared times 10 to the 1st. That's just rewriting a bunch of multiplying using our commutative properties. So that's this times this, and then when you multiply powers, you just add their exponents. And so that's the intuition. I just gave it to you. Sorry. So 2 times 3 is 6. 10 to the 2nd times 10 to the 1st is 10 cubed. And that's our answer. You multiply the first part, add the second part. Now this one is in scientific notation because this number is still between 0 and 10. There'll be some examples on the next page where it's not between 0 and 10, and then we have to do one extra step. Okay, here we multiply our 1 times our 6, and here we add our exponents, 10 to the 13th. Now here dividing is just a little bit opposite of multiplying. Here you you divide, instead of multiplying, you divide the first part and you subtract exponents. Okay, and why is that? Because the reason is because we take 6.0 times 10 to the 8th over 2.0 times 10 to the 4th, and then we can divide those guys, and then we can divide these guys, right? And so our answer is 3.0. 6 divided by 2 is 3.0. And when we divide numbers when we divide powers with the same base, we simply subtract their exponents. So that's 10 to the 4th. And likewise over here, it's 9.0 divided by 2.0 times 10 to the 5th over 10 to the 5th over 10 to the 10th. And so that's equal to 4.5 times 10 to the 5 minus 10 is negative 5. And we're done. Again, all of these numbers are in scientific notation because when I multiplied or divided, the numbers, the first part stayed between 1 and 10. Now on this next page, that's not true. Not true. So now we're on scientific notation, a little more complicated stuff where we have to do one extra step that we learned about in class today. So let's make sure we understand that. So we're going to do our same multiplication, and we get 24 times 10 to the 5th. Now the problem here is that this number on the left is too big. So we need to rewrite this as we did in class. We need to rewrite this left side in scientific notation, 2.4 times 10 to the 1st. Now that's times 10 to the 5th. We move this guy down, and then we need to consolidate those powers just by adding the 1 to the 5, and we get 2.4 times 10 to the 6. Similarly, when we multiply down here, and I've told you that 1.7 times 7 is 11.9, so when we multiply those, we get 11.9 times 10 to the negative 3 plus 4 is 1. Well, 11.9 is 1.19 times 10 to the 1st. And that we bring down our 10 to the 1st here. And we get 1.19 times 10 squared. Similarly, when we divide, we have to say, well, 1.0 over 8.0 times 10 to the negative 1 over 10 to the 0. Well, 1 divided by 8, as I tell you up here, is 0.125. Negative 1 divided by 0 is 10 to the negative 1. Well, our problem is that 0.125 is not in scientific notation because 0.125 is too small. So we need to rewrite it in scientific notation. And I carry this one down, and we get 1.25 times 10 to the negative 2. Similarly here, we're going to do our division, 2.0 divided by 4.0, which is a half. We can already see that's going to be a problem, times 10 to the 4th. And we're going to subtract our exponents here. So 2 divided by 4 is 0.5. And then 10 to the 4th minus 10 to the 10th is 10 to the negative 6. 4 minus 10 is negative 6. Well, this is too small, so we have to rewrite it in scientific notation. And that's times 10 to the negative 6. So we have 5.0 times 10 to the negative 7. Good, so that's scientific notation. Now we're going to move on to our final thing, which is radicals. So first of all, before we begin radicals, I want to go over the rules one more time and over the definitions. So this whole thing, square root of a, whenever I talk about square root of a or the square root of 7 or the square root of 10, these are all radicals. The whole thing is a radical. The thing inside, the thing that we're taking the square root of, is the radicand. So a is the radicand, the square root of a is the radical. So that's our definition. The whole thing is the radical. The thing inside is the radicand. Okay. Now, the thing we're going to do in order to apply our rules, and I'm not going to do them here. I'm just going to show you what some rules are that need to be fixed, is if you see the thing on the left, the situation on the left, we do the thing on the right. So if we see, so the square root of 20 is not simplified, right? We're talking about the 3 rules of simplification. Square root of 20 is not simplified because there is a perfect square factor in the radicand, right? Inside 20, 20 has a perfect square factor of 4. So in this case, we're going to separate this thing out into square root of 4 times the square root of 5, and then we're going to keep going from there. But that's the step that we do. We separate into 2 radicals. Similarly, if we have a fraction in the radicand, like here, we have a fraction. 1/9 is the radicand, so we need to separate that into 2 radicals, one divided by the other. Square root of 1 divided by the square root of 9. So that's how we separate, and then we go on from there. Finally, there's no radical in the denominator. So an example of that would be the square root of 2 over the square root of 7. Well, here we're going to have to rationalize the denominator by multiplying both sides by the top and bottom, the numerator and denominator, by the square root of 7. Multiplying by 1, square root of 7 divided by square root of 7 is 1. So it doesn't change the value, but it's going to get rid of the denominator, get rid of the radical in the denominator at least. Now the other thing to do is whenever we use these rules, we want to apply them in order from 1 to 3. We want to do 1 first, 2, then 3. We don't want to start down here because we can end up with bigger, hairier, scarier numbers. So always go, you can apply any of the rules whenever you want, but I'm telling you that the best thing to do is apply them in order from 1 to 3. All right, now let's look at some easy ones going to some more difficult ones. So here, our problem is that we have a perfect square. We have rule 1 broken. So we're going to separate that into 2 radicals. Multiply together, square root of 4 times the square root of 5. We take out the perfect square out of 20, and then whatever's left over, we put in the second radical. So that's 2 root 5, because the square root of 4 is just 2. So there we've simplified that radical. Now one thing I'd like to write down on the side of the page whenever I do these is all my perfect squares. Squared, it's 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and 7 squared. And you can keep going if you want, but this is usually good enough for our purposes. So again, I can see that 4 goes into 20. And so I used 4 in this first case. Now over here with 48, I like to go from greatest to least. 49 doesn't go into 48, 36 doesn't, 25 doesn't, but 16 does. So I can rewrite this as the square root of 16 times the square root of 3, and that equals 4 root 3. I could have done this. Let's see what would have happened if I would have done square root of 4 instead. I'd get square root of 4 times the square root of 12, which is left over, and you get 2 root 12. Now the problem here is that the square root of 12 has a perfect square inside it, so I have to keep going. So I go square root of 4 times the square root of 3, right? The square root of 12 is the square root of 4 times the square root of 3, so I have 2 times the square root of 3, which is equal to 4 root 3. So I get the same answer. It's just a longer path. So that's why I like to use the biggest thing first, the tallest one first. So okay, so that's how we do simplification of rule 1. Now rule 2 says we have to split this guy into 2 fractions, or sorry, into 1 fraction with 2 radicals. So you take the top part and put it under a radical, and take the bottom part and put it under a radical. And now I can go about rule 1, which is 1 and 3. Square root of 1 is 1. Sorry, what am I doing? So the square root of 1 is 1, and not square root of 9 is 3. Okay, here it's not going to be quite as simple. We got to go about separating into 2 radicals. Well, on the bottom, square root of 49 is 7. And on top, we have to go back to rule 1. And so 16 is our biggest integer, perfect square integer, or perfect square that goes into 32. So we get square root of 16 times square root of 2. And square root of 16 is 4 root 2 over 7. Down here, I have this 2 on the outside. I don't want to lose it, so we're going to keep that here. And then we're going to split our fraction into, or split our radical into 2 fractions. And so here we get 2 times the square root of 27 over 4. I can cancel these guys and get a 2 on the bottom, 1 on the top. So now I have the square root of 27 over 2. Well, the square root of 27 still isn't done because I can take out a 9 out of that guy. So that's the square root of 9 times the square root of 3 over 2, which is equal to 3 root 3 over 2. Okay, now let's get into the final page, and this is the hardest page, perhaps. Now let's look at this guy. Well, let's try rule 2. Separate into 2 fractions. Now we have to rationalize what they do to rationalize the denominator. So now we multiply by square root of 7 over the square root of 7. That's equal to the square root of 98 over square root of 7 times the square root of 7 is just 7. Well, square root of 98, let's write our numbers down over here. 4, 9, 16, 25, 36, 49. Well, 49 goes into 48, or 98. So that's the square root of 49 times the square root of 2 on top over 7. Well, square root of 49 is 7 root 2 over 7. Cancel, and we get root 2. Wait, that's pretty darn simple. Looks like I maybe could have done something different up front. Well, yeah, I could have just, what if I just divided those guys? 14 divided by 7 is just the square root of 2. Oh my goodness, I did all that work and got the square root of 2. Well, if I would have seen this, I could have taken the shortcut. Well, I went the long cut just to play with you a little bit and to show you a lot of cool tricks that we used every single step, all rule 1, 2, and 3 to do it this way. All right, B is square root of 20 over square root of 27. Well, we've done both of these really already. So this is square root of 4 times the square root of 5 over the square root of 9 times the square root of 3. Well, that's 2 root 5 over 3 root 3. Now, when we're here, do not multiply by 3 root 3. This is a common mistake over 3 root 3. You might do that because that's the denominator, but you don't have to do that. You just have to multiply by the radical portion over the radical portion. And so on the bottom, we get 3 times the square root of 3. Well, the square root of 3 times the square root of 3 is just 3. So we get 3 times 3 on the bottom. There's our first 3, and this is our second 3. And then on the top, we get 2 root 15. So our answer is 2 root 15 over 9. Over here, the rule is you multiply what's on the outside by what's on the outside, and what's on the inside by what's on the inside. So we get 6 times the square root of 18. Well, square root of 18 it breaks rule number 1. There's a perfect square inside it, which is our 9. So this is 6 times root 9 times root 2. Well, root 9 is 3, so that equals 6 times 3 times root 2, or 18 root 2. Here on D, we get 4 root 50. Well, 50 is 25 goes into 50, so we go 4 times the square root of 25 times the square root of 2, which is equal to 4 times 5 times the square root of 2, which is equal to 20 root 2. Now E, we have to solve this one first. So we take this square, we make this the square root of 2 over the square root of 3, multiply by root 3 over root 3, and we get root 6 over 3. So we multiply that by the square root of 6. Well, the square root of 6 times the square root of 3 over 3 is equal to the square root of 36 over 3, which is equal to 6 over 3, which is equal to 2. Nice. This one worked out really cool. You could have done it another route, and you could have said, well, let's multiply the insides together first. And you could have said, well, that's the square root of 2/3 times 6, which is equal to the square root of 4, which is equal to 2. Could have done it that way, but you get the same answer either way. All right, now we're done. And we're coming back to me, and we're going to just say that was all examples, almost all examples. So let me know if this works better for you. We worked probably 30 examples in this lesson, and very little explanation. The explanation we left for class. Lots of examples for this video. Tell me how you like it. Over and out.